So thank you all for coming back. And just let me start by saying that the chat has been disabled at the Zoom meeting because otherwise it pops up and it kind of ruins the recording. So if you have any questions, please open your microphones and I will be able to hear it, I guess. So yeah, let's continue with geometric topology of three manifolds. And yesterday we had come so far. We started with a node question. What are all the closed orientable three manifolds? And then we understood that, well, there is definitely no easy answer. And this guy called Henri Poincaré, he was trying to understand the same question more than 100 years ago. And he develops topology, he introduces several concepts, and he concludes that, yeah, there's really no easy answer, even for the simplest question that you can possibly ask. Simplify the question, what are all the closed orientable, simply connected three manifolds? And this became a conjecture, a Poincaré's conjecture, that the only example of such manifolds is going to be S3. So, and this conjecture remained open for exactly 100 years to know that this is a really hard question. Okay, so development of the theory to try to explain what are all closed orientable three manifolds goes like this. You start with the prime decomposition theorem by Nasser and Mueller. Nasser found the existence of this decomposition and Mueller proved the uniqueness. So every closed orientable three manifold can be uniquely in the sense that if you have a minimal decomposition, it's going to be equivalent to any other minimal decomposition by isotopies. And you can express it as a connected sum of prime manifolds. Then you can see that prime manifolds are either irreducible or they are S2 plus S1, and then you have this corollary. You can express any manifold as a standard connected sum of irreducible factors and factors which are diffeomorphic to S2 cross S1. And then you keep on going, you look at the irreducible factors and you decompose them over tori, which are called the JSJ decomposition. I didn't go very far in this decomposition today. It will be basically the main focus of our attention. I will go back to it later with more details. But the important part is that this decomposition, it cuts your manifold into pieces which are either atoroidal, in the sense that they don't have any Z cross Z subgroups. Z cross Z is the fundamental group of the torus, right? So that's why they are called atoroidal, or they are cipher fibered. And yesterday we spent a long time trying to classify cipher fiber spaces and explaining what are cipher fiber spaces. And now we will actually classify these spaces. And then we return to the composition JSJ. Okay, so let's give examples of cipher fiber spaces. And I will start with this theorem by Seifert himself. So if you have a cipher fibration with orientable total space, so M is going to be orientable cipher fiber space, and it has possibly boundary, possibly empty boundary. So the fibration can be obtained through this process, through this construction. Oh, one quick note. I will make the slides available on my webpage after the course. So if you want to take notes or if you don't want to take notes, feel free. Later, I can send them to anyone who asks, but I will make all the slides available on my webpage. Okay, so they can be obtained from the following construction. Anything that is cipher fiber can be obtained in this manner. I will first describe the whole construction, and then I will make some comments about the steps, about the intermediate steps. So first we start with any surface that you want, and now I mean any surface. It could be orientable or not, could be non-orientable, and it could have boundary or not. So start with any surface that you want. And then you remove disks from the surface. You remove like disjoint disks. Let's think of them as open, well-behaved disks, not like really crazy disks. and you look at the complement of this disk. So this is going to be a compact surface with boundary. Now, sigma has boundary, has non-empty boundary. Then you will make one construction that this construction I will present in details, which will be the orientable S1 bundle over sigma. If sigma is orientable, this is just the product. It's going to be just sigma cross S1. And if sigma is non-orientable, the construction is a little more subtle, and I will present it with details. So take this space. It's going to be orientable. It's going to be compact. And each component in the boundary of this bundle is going to be a torus. Right now, I am trying to ignore the boundary components that come from S, and I will just think in the boundary components that come from this disk's DI. This is what I'm thinking of the boundary of N at the present moment, okay? And each boundary component is going to be a torus, which will be this circle boundary of DI cross S1. And
I have a question.
Yeah, sure. Yeah.
I have a question. We start with a compact surface. Yes.
You can start with a compact surface, but might have boundary.
Might have boundary. Okay. There is no puncture.
There is no puncture. No. It's a boundary, really a boundary. It's going to be a closed surface. No, not closed. Compact.
Compact only. Okay. Thank you. Fine.
Sure. And then you have this total bundle, and this N is going to be a cipher fiber space. It's going to have this S1 decomposition over, and the base space is going to be exactly sigma, but you don't have any singular fibers. So if you want to construct any cipher fiber spaces, you need singular fibers. You need to allow them. So the point here would be to fill these components. You have torus, and you have to fill to the inside the torus components, adding singular fibers. So you fill the boundary tori using something called then filling. I will explain what that is. And you add the singular fibers in a compatible manner with this cipher fibration structure that you already have from sigma. Yeah, so the fibration that you have over sigma will extend. So these are the 4 steps. Step 3 is the longer one. You have 3 sub-steps. So let's explain this construction. So first, start with your surface sigma. And if sigma is orientable and is just a product, so let's ignore this case and let's focus on the non-orientable case. So think of sigma as a non-orientable surface. And here in the picture, I have a Klein bottle. So this is a Klein bottle. We have here this side identified with this side with the same orientation. But now we have this left side identified with the right side with the opposite orientation. So here in this example that I will use to motivate to the understanding of everything, it's going to be a Klein bottle. And actually, this example is really important for other constructions that will appear later today. So first, we know that any surface with or without boundary can be obtained from a disk in R2, a topological disk, with some sides identified. Think of a polygon. Think of a polygon in R2, and you will glue sides to sides, orientations reversed or the same, and some sides can be not identified to create the boundary of the surface. And you can always do such a construction. So you will look just at this disk by now. You ignore the identifications. You keep them in the bottom of your head, but right now let's ignore the identification and just let's look at this disk. In the case of the Klein bottle, it's going to be a square or a rectangle. Now you label the sides with the identifications that you will need. So here I am thinking A1 is going to be identified with B1, A2 is going to be identified with B2, and you could have other components C that would create the boundary, and they are not going to be identified. So you take this disk, and now you look at the product of this disk with the interval 0, 1. And this is a I bundle over the disk. Like you have points and you have interval, 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 like the most trivial thing that you can create. Now you think of the identifications that you will need. In this example, I will identify the red side with the red side and the blue side with the blue side. So you will have this AIs cross I and this BIs cross I and some CIs cross I, and you just look AI with BI, AI with BI and forget the CIs. Now is the step where things get a little complicated. You need to think of how is the orientation of each identification. So here, if this side here is identified with the bottom side, and in the identification that will create your original surface, the orientation is in some sense the same. So like the Klein model, there's two sides that are identified the same. The vertical lines are going to be identified with the same orientation. But if you have these other sides where the orientation is going to be reversed, you need to further reverse the orientation on your sides. So when you create this manifold, you will have a globally defined orientation. So just think of the right-hand rule or something. If you have a side here, which will be identified with this side, it's okay, you keep this vector. But if this one would be identified with this one, then you need to flip, basically. So you either reverse or you maintain the orientations on the sides, and what you create is actually orientable in the end. And one thing that is worthwhile mentioning is that at least one side has a reverse orientation, because otherwise you have the product. And if you have a product of something non-orientable with an interval, you have something non-orientable. And we want to create something orientable. So this process creates this structure here, the twisted I bundle over your non-orientable surface sigma. It's twisted because some of the sides are twisted. And it's not a product structure because it is orientable. So it cannot be a product. Okay, so this is the construction of this manifold, but I really want to understand this a little bit, because if you just say these things, well, this is a well-defined construction, you probably can prove that it is in fact orientable. But in my case, it took me a while to actually picture this. What is going on in this manifold? So let's try to understand it a little better. And also, we need to understand how to obtain the S1 bundle, right? We want to create sigma times S1, not times I. Yeah, I forgot to mention. So let's understand this manifold, and with this understanding, it's going to be reasonably easy to create sigma y tilde act times S1. So first, let's look at this central horizontal slice. The sides of this central thing are identified with themselves, because you either preserve the orientation and then the middle will be identified with the middle, or you reverse the orientation. And again, the middle is identified with the middle. You have this, you meet somewhere. So you have this copy of sigma. Right in the middle of your manifold, you have this green copy of your sigma, because remember, right now we had a disk and we were thinking of the identifications of the disk that creates sigma. And these are exactly the identifications that you will see here in the central piece. So this will be the core of your bundle. Any fiber passes through this core exactly once. And that's why this is actually a bundle over sigma. You can pinch any interval into sigma. Okay, so let's look at the other slices. Let's see what happens with these other slices. I just simplified the picture here to make it easier to look at. What happens to this slice where x is like larger than 1/2? First, if you have two sides which were going to be identified with the same orientation, you have lines inside the slice that are simple closed curves. Like this black curve here is a simple closed curve. It starts here, it ends there, but this side is identified with this side without change of the vertical orientation, so it's a simple closed curve. But if you have sides that are identified with opposite orientations, you start here with this pink curve, and this is not closed because this side here is identified with the left side with the opposite orientation. So this curve actually reappears on the other side. It reappears on the slice 1 minus x if we are taking coordinates. And now this is a closed curve. Now this is a closed curve because this side is going to be oriented with the other side with the opposite orientation, and then you close it up. So here, this blue thing is actually a double cover of your green thing. This blue thing here, in this picture, this blue thing is a torus. It's not going to be a Klein bottom. It's going to be a torus. You have the black curve, S1, and you have the pink curve, S1. And you can easily see that this is a product and that the sides are identified with the same orientation because you like flip the orientation twice. Here on this blue curve that is showing, you are reversing the orientation. But again, on this curve that I'm not showing here, you are again reversing the orientation. So actually the orientation of this curve, of this black curve, if you point it like in one direction, you will see that is coherent everywhere. Of course, it's going to flip, but then the other side is also flipped. So this is a torus. It's a double cover of the Klein bottom. And this is not an example for just the Klein bottom and the torus. This would happen in general. These slices are identified, the sigma times x, identified with sigma. Identified, no, they are connected. They are not identified, just the boundaries are identified. So this slice here is identified with this slice here. And when you move x, you see that it's just orientable and a double cover of your middle surface. So this is your line bundle. So now we understand
I have a
this
question,
orientable line bundle. Yeah.
Yeah, this pink curve may not be simple.
No, it's simple. It's simple. It doesn't intersect itself.
Okay, okay. This pink one.
Yeah.
If you twist it, so somewhere it cannot be intersect.
It will intersect the black curve.
Okay, okay, okay. Oh, so yeah, yeah, correct.
But not itself.
But not itself. Yeah, correct.
Now, yeah. So what's going on in this fiber bundle is that you have your non-orientable surface being double covered by several slices, and then you have a boundary. And this boundary, what is this? Let's look again to size this. Oh yeah, okay, let's show that it is a I bundle. So in this slice, you have any point here, you have this I, this interval I, and this interval I has boundary on the boundary of your manifold. That's basically it. You have boundary a torus in this example, and the central Klein bottle is the core Klein bottle. So this is not a closed curve. I know that I used to use this notation to make it like this is the same point as that, but they are actually distinct points. This is an interval and intersects the central just once. This is basically to show that this is actually a double cover, because this interval, it has boundary on the same connected component, which is this slice, sigma times 1 and sigma times 0. So this is the same torus component, is the boundary of your manifold. Your manifold will have boundary, which is this double cover of your central sigma. It could have other boundary components that come from the sides CI, but let's think of this without boundary coming from sigma so far, because it's easier. Okay, so to create your S1 bundle, you just use these fibers and you glue two of them together using this interval and another interval with the same point, with the same base point. And now it's something like you start here, you go there, you reappear here, you go down and you connect back. So now this is going to be an S1. And here in the middle, you have two core non-orientable curves. You have two copies of your Klein bottle, and each copy is going to be double covered by this other slices. It's more or less like this. Think of a torus double covering Klein bottle, and then you then go to the other way around. Again, this is probably funny, so I should stop doing it. But yeah, so this is your manifold N. This is your manifold N, which is sigma twisted bundle, this twisted S1 bundle over sigma. What is important of this manifold is that it is orientable. It is an S1 bundle over your surface sigma. And this asks yesterday's question. Now you have any surface non-orientable, and you can have this bundle over the surface, which is a cipher fiber thing because you have circles. And the basis space is going to be a surface. It's not trivial, and it's not an orbifold in the sense that it has no singularities. It doesn't have components. In the orientable case, it's going to be the product. Yeah, in the orientable case, it's going to be the product. There is no. Actually, you can make the twisted bundle for orientable surfaces, but then the total space will be non-orientable. If you twist the sides when you have orientable things, you can create something non-orientable. Okay, so this slides kind of showed step 3. We have this N space, which is orientable, compact. Each component on the boundary is a torus, and they are these boundaries of these disks. And it's a cipher fiber space over sigma, but without singular fiber, because all the fibers look the same. All the fibers are exactly the same. So you don't have singular fibers so far. Now let's go to step 4. And to go to step 4, we need to understand what a dense filling is. So let's work with dense fillings right now. And one thing that is important, dense fillings work for any trimanifold with toroidal boundary. If you have a torus component on a trimanifold, you can do dense filling. It doesn't have to be these examples. So it's a construction quite general. Okay, so take your trimanifold with a torus boundary. And the idea of dense filling is to fill. It's a filling, to fill past this torus. It's to glue a torus, a solid torus, to this boundary component. So this torus is no longer a boundary component, but it's going to be on the inside of your next manifold. So it's basically a connected sum, but instead of using balls, spheres, you use tori, but a very special gluing because you are gluing a solid torus. So this generates a new manifold. I'm calling here N fill, and now T is in the interior of this filled manifold. And the problem, and here problem is quote unquote, is that you don't have a standard way of doing that. You can do it like in infinitely many ways. And you just need to choose a gluing diffeomorphism from the boundary of the solid torus to this boundary component T. And actually, this is not a problem. Actually, this is an advantage because you have choice. And you can do it in some ways to make this new manifold to have some property that you would like. Dan was working with hyperbolic manifolds. He wanted to create compact examples from non-compact examples, and Thurston showed, I guess, that you could do it if you did it right. So he used this advantage. Okay, so now to make this clear, to make this advantage, how to say that, tangible, to pick this advantage on our hands, we need the concepts of slopes. So slopes, let's talk a little about slopes. You take the flat to torus. So now it is a product. It is S1 cross S1 with a metric. And we can think the universal cover of this torus is the map from R2 to the torus, which just winds around. I have here R2, here another, sorry, I have here R, I have another R here. And when I go horizontally, I am winding up the first factor. And when I'm going vertically, I'm winding up the second factor, and at the same speed, just to make everything cool and a square, a model of a square, like side one square. Then what happens to these lines in R2 of slope alpha? Any number alpha, you take a line y equals alpha times x in R2, and you push this line on your torus. What maybe you know probably is that this curve descends into a simple closed curve if and only if this slope is a rational number. If this slope is irrational, this curve here would go like dense on your torus. It's never going to close up. It's going to be a dense curve. But if it is a rational slope, then it will close up nicely to a simple closed curve. And then by analogy, we say that a curve in the torus has slope alpha, a rational number, if this curve is homologous or homotopic or isotopic, in the torus, the same thing, to this projected curve from R2. So this is the notion of slopes in the flat torus. And that's important because here we have a metric and I am defining something in something that is not quite abstract. Okay, so we need to overcome this when we are working with abstract tori. So, oh yeah, and we also think the case alpha equals infinity would be just the vertical line, and this vertical line is easily seen as one of the two factors, and this is going to be the slope infinity curve. So yeah, pictures, picture time, you know I like pictures. So this is a slope 0 curve in the flat torus, and we will call this curve the M curve. M goes for meridian. We will think of this curve as the meridian of your solid torus. And we have a slope infinity curve. We will call this curve L for longitude. So we have a meridian, we have a longitude, and now we have any other rational slope that you want. This is an example of a curve slope 3/2. This is a curve of slope 1/3. And you see that, how do you know that this is a 1/3 slope curve? You just count the intersections of this curve with the M and L curve. For instance, this curve here intersects the red curve, the M curve, just one time. So 1 is the coefficient of L, but it intersects the green curve in 3 times, in 3 points. So 3 is the coefficient of M. So this is a slope 1/3 curve, and it is homotopic to 3M plus L. I am almost lying to you because you actually need to take into account orientations. Like these two curves they are obviously homotopic. They are the same curve in the fundamental group, right? But this one intersects the red 1 time and this one intersects the red 3 times. So yeah, you need to take account orientation. So this will be like counting +1, this would count -1, and this would count +1. So there is a little more subtlety to make this counts work. Also, if the curve were going downstairs, let's say it, you would have to count -1. You also have notions of negative slopes, right? So it's not just counting the intersections, you need to count intersections, taking into account the orientations of the curves. You will define positive bases and so on and so forth. Okay, so this is also a 1/3 slope curve. Now we can give the definition of depth filling. So let N be a non-compact manifold with this toroidal boundary, one torus component. You choose one of the components in the boundary of a manifold, and you choose something to be called a meridian, something to be called a longitude. So you need generators of the fundamental group. And this is the hard part. This is the hard part, to have a well-defined notion of meridian and longitude. Once you have that, everything is standard. So this have a definition of slopes. You have a rational number or infinity, and we will think of infinity as 1 divided by 0. And this is the curve S times M plus R times L. And for a slope, you choose your slope, and the depth filling is going to be made with respect to that slope. You choose your rational number or your infinity number, and the depth filling associated to this number is going to be by the gluing diffeomorphism that maps the boundary of your disk. You want to glue a solid torus. Remember that. You want to glue a solid torus. And solid torus have a disk. I told you last time. Never forget that a solid torus has this disk. And now you will glue the boundary of this disk to the curve that you chose of slope R divided by S. Okay, so what? Here's the thing. When you do that, this curve, this slope R divided by S curve, it was non-trivial on the boundary of your manifold. But now it becomes the boundary of a disk because you're gluing a disk there. It's not easy to see. It's not easy to actually see because we cannot imagine a disk because the boundary goes around a solid torus in R3. It doesn't exist actually in R3. But in the abstract sense, it does exist. And now this curve, which was going around, is the boundary of some disk. So it's trivial in homology. So that's probably the most important feature of the depth filling. You choose one curve that you want to kill in homology. And you basically just kill this curve and multiples of this curve. Anything else will remain non-trivial. Okay, so let's go back to our construction. Remember that we still need to do this meridian and longitude choice. This, I told you before, is the hard part. And let's make this choice. Recall, we started with a compact surface. We removed disks from it, and now we have a compact surface with boundary that was sigma. And we constructed this bundle if sigma is non-orientable, and the product if sigma is orientable. I should have said something about orientable case here, I forgot. So each component of this space, of the boundary of this space, is a torus and comes from a removed disk in S. Again, I am ignoring that S could have boundary to start with, but it's the same thing. And we want to fill those boundary components of N using depth filling. Introducing singular fibers to the cipher fiber space. Yeah. So two important details, and obviously they are far from being details. We need the notion of slopes. So we need this well-defined geometric notion of longitude and meridian on any torus. And we also know that N already has a cipher fibration structure. So we want that the next structure, when we do dent filling, to be compatible, to extend towards this solid torus here that I am adding. So from the construction that we have, we know that there is a global cross section. What is a global cross section? Is the green thing, is the copy of sigma in the middle. You have a copy of sigma that each fiber goes exactly one time through that copy. You actually have two, right? But you in particular, you have one. And yeah, that's the picture. So the definition of a cross-section is this, that sigma is continuous and it's a right inverse for the projection. And we may use this in our construction. So before, let's now draw a hole, because we so far we were forgetting the disks. Now let's add a disk to our construction. The construction is exactly the same. And we still have this cross section here. Now let's think of S minus one disk. How do we use this cross section to define a meridian officially? We just define it as the inverse of this boundary. So remember, sigma, we have this projection from N to your surface sigma, and we have this cross section from sigma to N. So we have a torus in N, in the boundary of N, and we may look the inverse image of this torus by sigma. Now it's a curve in sigma, and then you project it back to your original manifold. And that's going to be your M meridian. That's going to be by definition your meridian. And a longitude is just a fiber. So now you have a standard choice of meridian. Now you have a standard choice of a longitude. And what's more important, it's compatible everywhere. If you have more holes, if you have more disks removed, the construction is going to be the same. You would have the same longitude. The longitude is just a fiber. And the meridian is just this holes in the same cross section that you start with. So everything is compatible to make the dent filling. Okay, so slopes are well-defined in this boundary component, and they are well-defined in any boundary component. In our example, this might be harder to make in other abstract manifolds. And now you choose your slope, and you don't want this slope to be infinite. The infinite slope here will be the curve L. So you just don't want L to be your curve that you will kill in homology. And you do the dent filling using this curve. Okay, now comes the beautiful part. In this new manifold, now think of this manifold as this torus here is filled. Now this is filled with a solid torus, and this black curve somehow is the boundary of a disk. And we have another copy, right? Never forget that we have another copy that goes the other way, but this is everything we need to understand. In this new manifold, the fibers were the vertical lines, like this L line, the longitude line. These were the fibers. And this blue line intersects your slope R divided by S curve exactly S times. This curve intersects the boundary of the disk exactly S times. So if you just push it a little bit to the inside, you will see the same picture. You are intersecting the boundary of a disk S times. So you push it a little to the inside and you will intersect the disk S times. So the fibration extends. this vibration is going to extend towards this solid torus here. Just like the example from yesterday. Yesterday, we had a curve, a PQ curve in the boundary of a solid torus, and we push it to the inside. Because now, from the point of view of the solid torus, that's what's happening. From the point of view of your solid torus here, you have some curve on the boundary, and you are pushing this curve to the inside. In this picture, this curve is vertical and straight line. But on our solid torus, this curve is something that goes around. And now the vibration extends, not only extends, but we understand this vibration is exactly the structure of a TSR vibration over the solid torus. And now we added one cone point of angle to pi over s. Okay, let's organize. Let's organize this. This is a process where you take your cipher fiber space N with a torus boundary T and a rational number R over S, and you create a new manifold, N1, where, well, we already said that N is the total space of a cipher vibration, and it has a section. And it has a section. This was important, the section. And sigma is S with any disks removed. Now, T is a component of the boundary. This is just a rational number, R divided by S. And N1 is obtained by then filling this boundary component we chose using this curve here. Oh, this was supposed to be L. Sorry, there's a misprint here. S times M plus R times L, and satisfies that the cipher vibration extends to another cipher vibration. The base space is now an orbifold with one cone point. And we have another n-1 disks to be filled. And also, there is a global cross-section. Because you have this disk, right? The fibers intersect only one time, even inside this disk. And now we have an extension of the global cross-section. Conclusion, you are in the same setting again, so you can repeat the process. You take three things, create a new thing with the same properties, so you can do it again. And you can do it again, you can do it again, you can choose n rational numbers and generate a cipher fiber space with the notation M of S, S is your original surface, and n rational numbers. And it will have a cipher vibration over an orbifold homeomorphic to your original surface, and Don would be freaking out if he was here today, because it's always homeomorphic, right? But the structure is the ones of cone points with multiplicity Si. And this is the definition. Okay, there are probably 11,000 questions at this point about this manifold. Like, is it well defined? Because several choices, right? Especially about the order. What if I had chosen a different torus to start with, and then I did it in another order? So the classification of these spaces is basically the following. With the notation introduced, every compact orientable cipher is isomorphic to one of these models. And we know that if we have a trivial component, like we add a zero thing, nothing changes. We can make a permutation of these choices and nothing changes. And we have a classification when two of these things are isomorphic. Two of these things will be isomorphic if and only if, first, after a permutation of indices, and here why I am adding 0, 0, 0, because the number n could be different from the number m in principle. So that's why you have zeros here. I am thinking that n is larger and I am completing with zeros. So if and only if, after a permutation of indices, we have that this rational number is just this rational number plus an integer. That's what mod 1 means. And if your original surface had no boundary, and that's for me is the most important case, the sum of these rational numbers equals the sum of the other rational numbers. For instance, if you have ms 1/3, 1/2, and s has no boundary, this is going to be isomorphic to ms 4/3, and then you need minus 1/2. Because here I added 1 to the first number, so I had to subtract 1 from the second one. The sum of these numbers has to be the same. And it's basically an if and only if. Okay. So what else? Yeah, sure. And this number, the sum of the rational numbers, it's going to be a little very much important to the classification of something else later. The sum of these numbers is called the Euler number of the vibration. Do not make a confusion with the Euler characteristic. This is called the Euler number of the vibration. This number actually measures something. It measures when you have, in your cipher fiber space, if you have a horizontal surface, a surface that intersects every fiber. You can have them, you can have them if and only if the Euler number is 0, if all these rational numbers even out. If you don't have boundary, if you have boundary, you always have horizontal surface. Okay, so this is what I was expecting to do yesterday. Good thing that I stopped because I wouldn't have time to finish this construction, to finish this classification. So now we can continue. Any questions? Oh, sorry.
I have a question. So
yeah.
when you fill the manifold by Dehn filling, so is it again it will be a closed manifold or something?
It's going to be a closed manifold if and only if your surface you start with is closed.
Okay.
If the surface has boundary, your result will have boundary.
The manifold has a boundary, the original manifold, after gluing. Okay.
Okay, so let's take a look where we are at this point. We started with a closed tree manifold. Then we made this decomposition by spheres, and we obtained prime factors. After we obtained prime factors, we looked at the prime factors and we said, well, they are either S2 cross S1 or they are irreducible. And then we looked at the irreducible factors. These irreducible factors, we go to a further decomposition of them by toroid, the JSJ decomposition, and then you have the JSJ components. And these JSJ components, they are either cipher fibered or toroidal components, and the cipher fiber components are now classified. Yes. So we need to work with toroidal manifolds at the point. And okay, let's see if this gets us any closer to the Poincaré conjecture. Let's keep that in mind, just for fun. Yeah. So you start with your simply connected closed tree manifold, and then you decompose it by spheres into prime factors. Nope, it's prime already. Because if it weren't prime, the fundamental group would be a free product, and then it would be, it cannot be simply connected. So yeah, M is also irreducible because the other option would be S2 cross S1, and it's not S2 cross S1. So you decompose by JSJ components, and yeah, no, you cannot decompose by JSJ components again, because otherwise your pi1 will be something called a graph group. It will be infinite. And then you know that it's not cipher fiber because cipher fiber spaces are classified and none of them have trivial fundamental group. So it's going to be an toroidal manifold. Yes, we got to a conclusion that it has no Z cross Z subgroup. It's trivial already. We already knew that. So unfortunately, we are nowhere closer to reach a solution to Poincaré's conjecture. Yeah, just for stating a fun fact and a little disappointing and probably for topologists at the time, right? All this work, 70 years of work, and we are nowhere near to solving Poincaré's conjecture. Okay, so since we need to understand a toroidal manifolds, and these manifolds have a toroidal boundary, we need to work now with compact tree manifolds with toroidal boundary, which could be empty. This component, let me return a little bit. These components here, toroidal components, will have non-empty boundary unless they are already irreducible toroidal manifolds. Like you could have closed ones, then the JSJ decomposition would be trivial. You wouldn't have any toroid, then you are already closed. So in some sense, most of the time, these components will actually have boundary. Yeah, what do we want to define now? Oh, yes, right. So let sigma be a compact surface in a compact tree manifold now with toroidal boundary. First thing, we'll say that sigma is properly embedded if sigma is embedded and the boundary meets only the boundary of the manifold. First time I read this definition, I was basically, what? But sigma is compact. Why are you talking about proper? Because from my point of view, like geometric point of view, and basically the topological definition as well, right? Being proper means a compact on the ambient space intersects only a compact of your subset. And if sigma is already compact, it's always going to be proper, I thought. But the point is, we want to work with the interior of these manifolds. We are putting everything in a compact setting, possibly with boundary, but later the boundary is not going to be there. We will think just of the interior of these manifolds. So the boundary will go away. And if the boundary goes away and you have, like, for instance, let's think of the disk times R. It has this compact boundary, or times S1, yeah. It doesn't matter. This disk here is compact. But if I think this as an open disk, this will be proper. This will be actually proper. Then the boundary of the disk is going to be at the boundary of a manifold in some sense. You are going to infinity if the manifold is going to infinity. Okay, don't lose too much energy on this definition. Sigma is properly embedded if it is embedded and the boundary of sigma is the intersection of sigma with the boundary of the manifold. So sigma, the interior of sigma cannot intersect the boundary of the manifold, and you cannot have boundary of sigma on the interior of the manifold. Basically, that's the definition of being properly embedded when you are talking about compact stuff. Okay, so in this case, if you have a properly embedded surface, a compression disk for sigma would be an embedded disk in the ambient space with the boundary in sigma and the boundary not trivial in pi1 of sigma. Okay, let me maybe draw a picture. For instance, let's think of this torus in S3. R3 and S3 are basically the same. You just add a point to R3 and then it becomes the sphere, right? So here you have a torus. It's properly embedded because it has no boundary and it's embedded. And this would be a compression disk. this is a compression disk for your torus. It's going to be a disk in the ambient space. It intersects the surface only at the surface, only at the boundary of the disk. And the boundary of the disk is non-trivial in pi1 of the surface. That's a compression disk. So we don't like compression disks. If sigma doesn't admit any compression disk, then it's called incompressible. Okay, why this definition? Because this word had already appeared in our course twice, and I didn't give any notice about it. It appears in the JSJ decomposition. These tori, they have to be incompressible, because in some sense, if they are compressible, if this disk exists, oh, this is not original. So if this disk exists, you can simplify things a lot. You could take a neighborhood of this disk. A neighborhood of this disk would be a ball, and then you can cut along this ball. You can make things a lot simpler. So these tori here are incompressible in the JSJ decomposition. So let's take a little look, let's take a closer look to the JSJ decomposition theorem. Okay, we already know that this decomposition is by tori. These tori are non-trivial in the sense that they are incompressible. You cannot find a disk that simplifies the torus. And each component is either cipher fiber or a toroidal. And this is something I didn't tell you yet. Any two minimal collections of these tori are going to be isotopic. So you have a standard decomposition. And this is the definition of the torus decomposition of your manifold. Since this decomposition is now standard in some sense that any two minimal collections are isotopic, we can talk at the decomposition. So the JSJ decomposition with the minimal number of components is going to be called the torus decomposition of the manifold. These tori are going to be called the JSJ tori of your manifold. The components that you create will be called the JSJ components of your manifold. And now, yes, and this is something we need to address. What happens if you have this manifold here? T2 cross 0, 1. This cannot appear in the JSJ decomposition. If this component appears in the JSJ decomposition, then it has to be everything. The decomposition must be trivial. Because otherwise, what is T2 cross 0, 1? Torus boundary here, just a line field here. So if you have more than one component, you just glue this together with the next component. And then you have, again, a JSJ decomposition, because this, when you glue this torus times 0, 1 to anything, you don't change the topology. This is basically the same as a identity element for the connected sum. This makes the new identity element of this connected sum by tori. If you have like torus interval, you glue to the next one, it doesn't change the next one. So this component is a redundancy. So it doesn't appear in the JSJ decomposition. Okay, let's talk about one of my very famous mathematicians of all times. Did I say famous or favorite? He is one of my very favorite mathematicians of all times. William Thurston, Bill Thurston. He just asked a question. Okay, we don't understand the Poincaré conjecture. We are nowhere near proving it, basically. So what about geometrization? Is it possible to find model geometries for any closed orientable tree manifold? That's not exactly his question. His question he added here in 1982 as a conjecture. And the chapter 1 of this paper, the name is perfect. A conjectural picture of tree manifolds. I think that this is the case, basically. And he goes on a little bit and he states it like, I feel confident in proposing the conjecture that the interior of every compact free manifold has a canonical decomposition into pieces which have geometric structures. So instead of compact here, let's think of closed. So he was saying that if you have a closed free manifold, you can cut it somehow, and each component is standard, is a canonical decomposition, and each component is going to have a geometric structure. So basically, what Thurston did, he was sitting on this table, on his desk, at his office. He looked Poincaré in the eye, and he said something like, yeah, I doubled the bet. You asked the Poincaré conjecture. I asked the geometrization conjecture. This conjecture is, it's groundbreaking. To ask the question, to have the guts of asking this question, when even the simplest case was so wide open, it takes like a lot of courage. This guy was, and not only that, he just didn't ask the question. For until the end of this talk, and probably a little bit of tomorrow, I will talk what Thurston actually did, what was his contribution to the geometrization. Okay, so let's start with the definition of a model geometry, because I already said, can we find model geometry? So what is a model geometry? From the algebraic point of view, a model geometry is a pair with a simply connected manifold and a Lie group acting on this manifold, with this action being transitive, which means any 2 points are joinable by this connection, by this action, sorry. You can take any point, any other point, and you have one action that takes this point to the other. The stabilizers are all compact. So if you have a point that is fixed by some actions, the set of all actions that fix this point is compact on the group. G has to be maximal. Oh, maybe later. G is maximal in the sense that you don't have a larger action on this manifold. And you have the definition, sorry, of equivalent model geometries. You have the definition of equivalent model geometries if there is a diffeomorphism from one space to the other space that maps the action of this group to the action of that group. On the third point, can you see again?
In the third point, it's not that G tilde has to act, but act transitively.
Yes, perfect. Yeah, thank you. Acts transitively with compact stabilizers. You need 1 and 2 as well. Thank you for pointing that out. Perfect. So, geometric interpretation of this definition for me is easier. And the interpretation is that X is a simply connected homogeneous manifold. What is a homogeneous manifold? Is a manifold where you have isometries, a Riemannian manifold, so now you have metrics, that any 2 points are connected by an isometry. So it's a space where it's really difficult to locate where you are, because everywhere looks the same. I'm here or I'm there, I don't know. It looks the same to me. Like every 2 points look the same. And G is going to be the full isometry group acting on this homogeneous manifold by isometries, of course. And if this group is contained in the isometry group of another manifold, then it has to be the other group of isometries. You don't have anything with the same base isometry structure. That's the isometry group of some larger. And 2 model geometry, this for me is the best feature of this interpretation that two model geometries are equivalent if they are isometric. So that's more simple. One question?
Yeah.
Good question. Nothing is obvious.
Yeah.
Go for it.
Like in general, if you have a simply connected manifold with a Lie group acting that way, can you define explicitly the metric for which it is isometric?
You have a way of cooking up a metric when you have an action. And this metric is going to be, G is going to be exactly the isometric group for this metric. So, but it's not too obvious. If you are compact, then you can just make an integral of everything. If you are non-compact, it's more difficult.
And this is questionnaire in Riemannian geometry now. Like I remember that if you have a Riemannian manifold of dimension n, then its isometric group or the Lie group, its dimension cannot exceed n times n plus 1 divided by 2.
Yeah.
So can we say that corollary of this is that the Lie group of dimension is higher than that, cannot act that way?
Sure, of course, because then it would not have compact stabilizers. The thing is, this assumption, let me repeat the question just so everybody asked, can hear. Let's make it strict to dimension 3, okay? Because 3 is easy. No, actually 3 is hard, but it's our example. Dimension 3, what does it mean the stabilizers are compact? It means that you are actually a subgroup of SO3, of O3 at least. You are a group of rotations of the sphere. And this group has dimension 3, at most 3. O3 has dimension 3. So if the stabilizer... I'll get it. What does it... Okay, maybe let me restart. When you have an isometric group, transitive, so you can change this point to any other point of your manifold. So you have at least 3-dimensional isometric group when you are homogeneous.
Yeah,
at least 3. But what is the maximal dimension you can reach on dimension 3? It's 6, because any isometry is defined by 1 point, and the derivative of the isometry in this point. And the derivative of the isometry in this point is going to map this orthogonal basis into other orthogonal bases. So you have an extra 3 dimensions. You can choose where this vector goes, and you can choose where the other vector goes. So you are a subgroup when you are fixing 1 point, when you are mapping this point to itself, the isometry is defined by a rotation in the tangent space of this space. And the group of rotations of R3 is 3-dimensional. So the maximal dimension you can have is 6. But okay, I will get there.
Okay, sorry for
No. That was super good question, and the moment was good too. Okay, so this is the definition of a model geometry. Now we need to define what is a geometric structure. And we say that a manifold is modeled on a geometry X if M is diffeomorphic to the quotient of your space X to a discrete group of G acting on X freely. And the way I said it, probably you know that I don't like too much this definition. I'd rather go for the Riemannian version of this definition, which would be X is a model geometry for a manifold M if M admits a complete metric such that X is the Riemannian universal cover of the total space of the Riemannian universal cover of M with that metric. It means that you have a locally homogeneous metric on your manifold, locally homogeneous. So for any point, you cannot distinguish nearby points, basically. And then when you lift it to the universal covering, it's going to be a globally homogeneous metric. So that's the definition of a geometric structure. And now let's go again for the geometrization of surfaces. This theorem I presented in the last class, that every closed orientable surface of genus G admits a metric of constant Gaussian curvature kappa. And we knew that kappa was positive if and only if the genus was zero, kappa was zero if genus 1, and kappa was negative if genus was bigger than or equal to 2. So what is a metric of constant curvature? In dimension 2, that's exactly a locally homogeneous metric. They are equivalent. So this theorem can be read as a closed orientable surface of genus G admits a geometric structure over a model geometry X, and we know who the model geometry is. The model geometry is S2 if the genus is 0, is R2 if the genus, if and only if the genus is 1, and is H2 if and only if the genus is higher than 1, so bigger or equal to 2. So this is the geometrization for surfaces in a new point of view using geometric structures and model geometries. So one thing that I need to clarify, the geometric structure might not be unique. You could have distinct groups that you quotient to obtain your same result, but the geometry is unique. So just to make it this clarification. Consequence, any closed orientable surface has a model geometry. And moreover, there are only 3 possible model geometries, which are the space forms of dimension 2, R2, S2, and H2. Okay, let's take a brief look at dimension 3. And it's not very difficult to see that a connected sum never admits a geometric structure unless you have RP3 connected sum with itself, which is a bundle over S1 and etc. It's a cipher fiber space over the projective plane with S1 bundle. And in particular, there are examples of closed pre-manifolds that do not admit geometric structures. So from dimension 2, that anybody had a model geometry, dimension 3, if you are not prime, don't even try. Don't even try to look at this. So, and even in the class of reducible manifolds, you can find manifolds that are not geometric, that do not admit any geometric structure. So you actually need to make a decomposition of the manifolds to obtain geometrization. And the natural candidate for these pieces are the JSJ decompositions. So the next questions are, do the JSJ components of a closed free manifold admit a model geometry? This is the next question, the next important question. And what are the model geometries of dimension 3? So let's make the definition of a geometric manifold. I already used that language, but I never defined what a geometric manifold is. Now, remember, we are looking at the JSJ components. So the JSJ components are compact manifolds with toroidal boundaries. So that's going to be the basic space to define geometric manifolds. So let M be a compact free manifold with either empty or toroidal boundary. We say that it is geometric if the interior of your manifold, so we ignore the boundary, if the interior of your manifold admits a complete geometric structure, so a complete locally homogeneous metric, in my point of view, of finite volume, and model on a geometry that admits some compact quotient. Okay, I think the first time I read this, I said, why aren't we stopping here? A geometric manifold is something that admits a complete geometric structure. I thought that would be reasonable, right? But we need this geometric structure to have finite volume, and we need that the geometry itself admits some compact quotient. So let me give you, oh, and the notation is going to be an X manifold. Let me give you a spoiler and also a justification of why we have these extra assumptions to call something geometric. We restrict to finite volume structures because we can. Basically, yeah, not really. Not only because of that, but also because when we restrict ourselves.
Yeah, I have a question. So
yeah.
Why we need the interior of him?
Because we don't like boundaries. We want that, we don't want to exit the manifold. A manifold with boundary, I'm looking at the, how to say that, the speaker, but I should be looking at the camera. When we have a manifold with boundary, yeah, it's like you can exit the manifold. You could be inside the manifold, you reach the boundary, and you go outside of it. So we don't like manifolds with boundary. We want this boundary to be at infinity. So we actually have to go through an infinite length curve. We have to spend infinite energy to exit the manifold. So that's the more natural way of doing it, looking at the interior.
Okay, so the natural question is if we attach the boundary, if we close up the manifold, then what is the geometry, model geometry of that? If we attach the boundary, suppose
then you might not have geometry.
Okay.
Because exactly that's the other way around that we are doing stuff. We are taking I'm looking again at the speaker. We are closing, we have a closed manifold, and then we are cutting it into pieces. So these pieces will have geometric structure. So if you close again, you might not have any geometric structure at all.
Okay. Okay. Thank you.
Okay. So not only because we restrict ourselves to finite volume, but also it helps to avoid some ambiguities. I will talk about this one ambiguity in maybe today. Okay, so also there exist geometries which do not admit any compact quotient, but they are simply not important to the geometrization, to the setting of geometrization. And Thurston actually noticed that you not only you don't care about these geometries, they are not important to the setting of geometrization. So let's talk a little about Thurston's work. The first theorem of Thurston, maybe not the first chronologically, but the first that I am showing you today, is that there are only 8 model geometries of dimension 3 that admit compact quotients. So they are classified. This is the list. Now I will present them to you. Okay, so let's talk about first 3 geometries. The first 3 geometries are the generalizations of the dimension 2 case. So R3, H3, and S3 with matrix of constant sectional curvature. 0, 1, and -1. Just some remarks about these spaces. They are the only called anisotropic geometries. What is an anisotropic geometry? Is a homogeneous space that not only you cannot identify where you are, you also cannot identify which side are you looking at. Like you are completely lost. You cannot say if you are looking north, if you are looking east, if you are looking south. There is no definition because any point is isometric to another point, but also any directions. They are all isometric. You always have an isometry that maps any point, any vector to another, any point, any vector. So these are the only anisotropic geometries. And that's equivalent to the dimension of the isometry group being equal to 6, the maximum possible dimension for dimension 3. Any S3 manifold, in other words, any geometric manifold modeled by S3, also known as elliptical manifolds, they must have finite fundamental group, and they are cipher fiber, because S3 is itself cipher fiber. You have Hopf fibration. And this vibration goes to quotients of S3. Any R3 manifold is a product. Let me rephrase that. R3 is a product, is R2 times R in several directions. And this product structure also has to pass to the quotients of R3, and they are called flat manifolds. And I think there are 10 different flat manifolds, and I'm not sure if 10 is orientable or altogether. And any of them are cipher fibered. All these manifolds are also going to be cipher fibered. And any H3 manifold, which are called hyperbolic manifolds. And now there are like a lot of hyperbolic manifolds, and none of them will be cipher fibered. You can never have a hyperbolic structure which is cipher fibered, and they will be instead toroidal components. Okay, so we have two generalizations, expansions, which are products. You have H2 cross R and S2 cross R. They are the two product geometries. And it's not difficult to see that they are actually geometries. You just need to look at the isometric groups and see that they are maximal. So these are the two. Sorry? I didn't listen. S1 times R2 is not simply connected. So it's not a geometry. And S1 cross R2 would be covered by R3. Because S1 is covered by R. So it's not anything that you want. Okay, so H2 plus R and S2 plus R are the two product geometries, and the remarks about it. They are not anisotropic because you can differentiate at least one direction. If you are in H2 cross R, you know that, well, this side is R. You can look at your point and you will be able to identify this is the R and this is H2. I cannot say where in H2 I am. I cannot say that because H2 is anisotropic, but H2 plus R is not. You have something to relate. I know that I am going in the R direction. I cannot say if I'm going up or if I'm going down because they are isometric, but I know that I am in the R direction. Same thing for S2 plus R. And any geometric manifold modeled by one of these two geometries is going to be cipher fibered exactly because they are a product. So you have this R factor, it will have to descend to S1, and you will see this S1 everywhere. So they are cipher fibered. And there are only two closed orientable manifolds modeled on S2 cross R, which is S2 times S1, or this little guy here, RP3, connected some with RP3, which is the twisted bundle of RP2 with bundle S1. Okay, now we have two more geometries, which are non-trivial R fibrations. So these geometries, they are R fibrations. Like you have a fiber R over H2 or a fiber R over S2. And now you have non-trivial fibrations over spaces. You have the Heisenberg group, which is called the Newtree group, endowed with any left invariant metric. Any left invariant metric here on this group is going to be maximal in the sense of isometry group. And some remarks, not this Heisenberg. Don't mess it up. The second one, the isometry group of Newtree with any left invariant metric has dimension 4. And it's the total space of a Riemannian submersion over R2. So you have a non-trivial R fibration over R2. And like a projection, I think this is the map. I think I didn't mess it up. X, Y, Z in the matrix, and you just project into this in this component. This will be a Riemannian submersion, but it's not trivial. And any geometric manifold model on Newtree is going to be cipher fibered because nu is fibration, an R fibration. So anywhere it closes down, this R fiber is going to close up, and etc. The other non-trivial R fibration is SL2R tilde. And I used to be scared of this space the first time I've seen it, because the whole notation would be PSL2R tilde. And I was like, oh my God, too many informations. But then when you start looking at it, yeah, it's not so bad. You start with SL2R, which is just the unit determinant matrices, 2 by 2 real entries. Then you go to projectivify this space. You quotient it by identity minus identity. And this is the group of Möbius transformations of the complex plane with real entries. And it can be seen as the isometric group of H2, which preserves orientation. And it has one canonical left invariant metric, which is induced by the tangent bundle of H2. This metric is called the Sasaki metric, or I'm not sure if I'm pronouncing it right, but it has one canonical left invariant metric, and we are thinking of SL2R tilde as the Riemannian universal covering space of this group PSL2R with this metric. And okay, remarks. It's a lot easier to think as this model. Like, just give me what's the word for this? An engine space and a metric. Okay, this is the metric. Okay, this is SL2R tilde. H2 here is going to be the disk model for H2 is conformal to the Euclidean metric with some conformal factor lambda. It's, if I'm recalling correctly, 4 divided by 1 minus x squared minus y squared. And SL uses this conformal factor here, and also here. Okay, so this is SL2R tilde. And here's very important to notice that it is different from nu3 in some sense, because nu3, any left invariant metric on that manifold would be a maximal isometric group, and they would be all equivalent, they will be all homothetic to each other. In SL2R tilde, it's not the same. You have like a 3 parameters family of left invariant metrics on SL2R tilde, of non-isometric metrics, left invariant metrics, and it's going to be a maximal isometry group if and only if 2 of the parameters are the same. So think of R3, and you have like a plane, a vertical plane. In this plane, you have maximal isometry group. If you are in other spaces, you don't have maximal isometry group, so you're not a model geometry. It's for this specific metric or this metric up to homotheties that you are actually a model geometry. And it is also like nu3, it is the total space of Riemannian submersion, but now instead of R2 is H2. The dimension of the isometry group of this space is also equal to 4. And any geometric manifold model in this manifold is going to be cipher fibered as well. Okay, and now the 8th geometry is sultry, and it is the least symmetric geometry. So sultry is a Lie group equipped with this group operation and that metric. Again, it's not all left invariant metric in sultry that will make it a model geometry. You need some metric with, there are metrics which are more symmetric than others. And the isometric group of sultry is the least possible dimension for a model geometry. It's just 3. And any geometric manifold model in sultry is going to be a torus bundle with pseudo-Anosov type. So I don't want to go into details here for this, is the exception. And any sultry manifold, it's not going to be cipher fiber or toroidal. Okay, let's summarize. The 8 geometries are the space forms, R3, S3, and H3. And here, red, this one. Red is gonna mean cipher fiber, blue gonna mean toroidal, and these are the geometries with maximal isometry group. You have the two product geometries, S2 cross R and H2 cross R, with isometry group having dimension 4. You have two non-trivial R fibrations, nu3 and SL2R tilde, 4-dimensional isometry group as well. And you have the other geometry, which is Sol3, the least symmetric geometry dimension of the isometry group equals to 3. And this gives rise to geometries, to geometric pieces, which are not cipher fibered and not toroidal. One little remark that I hear this question several times when I talk about geometries. What about E capital spaces? If you know what I'm talking about, great. If you don't worry about it. This is Riemannian geometry at its best. So E capital spaces are these 5 spaces, S2 cross R, H2 cross R, the Berger spheres, nu3, and SL2R tilde. And they are simply connected. They are all simply connected homogeneous free manifolds with 4-dimensional isometry group. And they are the total spaces of submersions over H2, R2, or H2, R2, or S2. So with constant curvature kappa and bundle curvature tau. That's why they are called E kappa tau. You have a submersion over some space of constant curvature kappa with bundle curvature tau. And here's a table of them. And many people think, well, why the Berger spheres is not in this list? Because everybody else is on the list, but Berger spheres is not. The thing is, the isometry group of the Berger spheres is contained in the isometry group of S3. You have the isometry group of the Berger spheres is a 4-dimensional group, and you have a subgroup of S3, of the isometry group of S3, where the Berger spheres are, the group of the isometry of the Berger spheres is there. So this is not a maximal geometry. You could extend the group of isometries of the Berger spheres to the group of isometries of R3. That's why they are not on the list. Okay, so in the last slide, in the last 2 slides, if you were really paying attention, you will think, wait a second. We know that the JSJ components are either cipher fiber or a toroidal. I've been telling this for a while now. So how can it be that Sol manifolds are neither? I did say it, right? The previous slide. Geometric manifolds that are not cipher fiber and not a toroidal. So what's going on? Actually, the blocks that appear in the JSJ decomposition are not going to be the geometric blocks. We need to deal with one special case. We need to modify this case to obtain geometrization on the blocks. And yeah, okay. So, and now we need to understand what is the geometric decomposition of an irreducible trimanifold M. Let M be a closed, irreducible trimanifold, and let Ti's be the JSJ tori and Ni's be the JSJ components. So we start with the JSJ decomposition. Now this will be a theorem. This is just to justify what's going on here. If no Ni is diffeomorphic to this I bundle, to this twisted I bundle over the Klein model, the one we had in the beginning of the class. If no component is diffeomorphic to this guy, then yeah, everything is going to be geometric and modeled in one of the first 7 geometries. But this compact trimanifold with toroidal boundary, orientable, this is not geometric. and it actually appears in the JSJ decomposition. This is a component that appears in the JSJ decomposition, but is not geometric. It admits a flat structure, so you can cover it by R3, but this structure will have infinite volume. So we don't want this piece because we want geometric structures of finite volume. So when it appears in the decomposition of some irreducible trimanifold M, we want to remove this component. How do we do it? Remember, this component, this manifold, has a torus boundary and this central Klein bottle. Now it's just one copy, it's not two copies. It's not going to be K times S1. It's just the first one, just K times I, tilde times. It has one torus boundary, and here you have a central Klein bottle. So I'm going to think at torus boundary, central Klein bottle, and here there's something else in the decomposition. There is another component, unless this is everything. If this is everything, yeah, there's nothing to do. But if there is another component, what we are going to do is we're going to glue these two together, and we are going to remove this central Klein bottle. Now the central Klein bottle will like open up and be at the boundary of this component together with this component. This gives rise, after we do this with every component, which is K times 0,1, this bundle, we have a new decomposition, and this new decomposition is called the geometric decomposition of M. Now we are not cutting just along tori, we are cutting along tori and Klein bottles. So each component will have genus 0 boundary. That's all you can say. And just like JSJ decomposition was standard, if you have a minimal number of components, the geometric decomposition is also standard. And now there are 3 pieces that never appear, unless they are the whole manifold. But if you are working with irreducible closed tree manifolds, you don't have boundary, and then these pieces can never appear. You can never have D cross S1 because this is compressible. Is this picture here? This picture here, basically. Yeah, D cross S1. It's compressible. You cannot have this kappa y tilde 0,1 y tilde times 0,1 because we are killing them, changing the central Klein bottle by this tori, and you cannot also have T2 times 0,1 because this component is redundant. If you have this component, you glue it back to another component, you don't change the topology of this other component. So these 3 manifolds never appear in the geometric decomposition. And now what happens is that any component that is left on your geometric decomposition is either cipher fiber, a toroidal, or a torus bundle. And now you need solid geometry. Okay, so I think I will stop right here. And tomorrow we continue. If you want to send me an email, this is my email. And this is my web page for whenever I upload the slides there, they will be on my web page. Okay, so thank you again.